Okay, and we're back. Today we'll be talking about induction, which is the last proof technique and probably the most involved one that we'll need to cover. Before that, a couple announcements. Homework 3 will be due tomorrow, just before midnight. Homework 4 will come out around then, and it'll be due next Friday. So the cycle continues. And this is pretty important. I didn't write it down. Your quiz. So the quiz will be a week from today. Again, 3:40 to 4:10. It'll be similar setup, 3 to 4 questions, but it will cover all the topics that we've done since the first quiz until Tuesday. So all proof techniques, including induction, will be on the quiz. Okay? And lastly, when we're talking about induction, we'll use this sigma notation very frequently. And if you haven't seen sigma notation in a while, or you just haven't seen it before, or you just want a refresher, on our textbook, which is linked on the site, if you go to the appendix at the bottom of the left scroll tab, there's one page that says sigma and pi notation. Click that, and it will walk you through what exactly this means and how you can manipulate some sums. Is that clear? Any questions with that? Okay. So before we get into induction, I want to go over this proof kind of just for fun. How many people have seen this before? Okay, so a few people, but not everybody. Okay, so what we want to prove is that the expansion 0.9 repeated is equal to 1. Okay, and the main idea behind this is that the sequence of 0.9 repeating 9999999 never ends. Right? If you pick, an arbitrary stopping point, let's say 1,000,000 nines later, sure, that would not be equal to 1. But the whole point is, the exact representation of this number is with this repeated decimal. Okay? And that exact representation is precisely equal to 1. Okay? So there's 2 ways that we can prove this. So the first way is a little more straightforward. Let's just say x is this number. Okay, and we also want to show that x is equal to 1. So one thing we could do is multiply this number by 10. Is that clear? Okay, let's see what happens. So we can have 10x. And what happens when we multiply by 10? We move the decimal place 1 to the right. So that would make this look like 9.9999 repeated. Okay? What can we do now? We can subtract the second equation from the first. What do we have on the left-hand side? We have 9x. On the right-hand side, the 0.9 repeateds cancel out, and we're left with 9, which gives us x is equal to 1. Okay? So this is one way to prove that. Let's look at another way. Okay? And this revolves around the fact that this almost goes back to our first lecture when we talked about representations in base 10. Right? So for example, the number 342 is just 3 times 10 to the 2 plus 4 times 10 to the 1 plus 2 times 10 to the 0. Is that clear? And we can extend that on the opposite side of the decimal, right, to negative exponents. So suppose we have 0.342. Well, we can write that as 3 times 10 to the negative 1 plus 4 times 10 to the negative 2 plus 2 times 10 to the negative 3, which we could write as 3 over 10 plus 4 over 100 plus 2 over 1,000. Is that clear? Okay, so let's apply this principle to our number 0.9 repeated. Okay, so let's look at 0.9999. Well, we can write this as 9 over 10 plus 9 over 100 plus 9 over 1,000 plus ... forever and ever. Is that clear? Okay. And we can actually write this as an infinite sum going from I is equal 1 to infinity of terms of the form 9 divided by 10 exponent I. Is that clear? we're taking 9 over 10 to the 1, plus 9 over 10 to the 2, plus 9 over 10 to the 3, so on until infinity. Is that clear? And we can actually common factor out the 9, because it's independent of the I. And now we need to think back to how to evaluate the sum of an infinite geometric series. Okay, and if you never learned this before or forget it, that's fine. If you go, I believe it's in the next chapter in the textbook, 2.3, we talk about this and derive this again, and we'll actually be doing this in class on Thursday. But for now, we just need to know the result. Okay, so the sum of an infinite geometric series. Also, we know this is a geometric series because each successive term is the last term multiplied by some number, right? We have 1 over 10, and then we multiply 1 over 10 by the common ratio, which in this case is what? Also 1 over 10, right? Because then 1 over 100 is just 1 over 10 times 1 over 10. 1 over 1,000 is just the last term, 1 over 100 times 1 over 10, right? Is equal to the first term divided by 1 minus the ratio. Okay? If and only if the ratio has absolute value less than 1. Okay, in this case, what's the first term? 1 over 10, and what's the common ratio? Also 1 over 10, right? So this gives us 1 over 10 divided by 1 minus 1 over 10, which is 1/10 divided by 9/10, which is 1 over 9. Interesting. So if we plug that into here, we get 9 times 1 over 9, which again gives us 1. Okay, so multiple ways we show that the expansion of 0.99 repeated is exactly equal to 1. Okay, does this really have anything to do with induction? No, but I just think it's interesting and something that you should be aware of. Okay, cool. So to recap the different types of proofs that we've seen, we started off talking about direct proofs, then we talked about proofs by contradiction and contraposition, and then last class we talked about proofs by cases and did several examples. And so again, as I mentioned, we're going to wrap up talking about proofs by induction. Okay, so what you want to be thinking of, or like an example to, like a real world example of this, is suppose you're sitting in a massive lecture hall or you're in a very, very long line and you want to know what spot in line you are. Okay? You could sort of step outside and like count 1, 2, 3, 4, 5, 6, 7, 8. You could do that and it would get you your result. But you could also follow this principle, right? The first person in line, by default, knows their position in line, right? Because they're the first person in line. There's nobody in front of them. And then we can use the idea that if you know the person in front of you's number, you know your own number, right? Because you just add 1 to the person in front of you. Is that clear? Right? And so if the first person knows that they're the first person, and additionally, at any point in the line, if you know the number of the person in front of you, you know your number, everyone can figure out their spot in line. Okay, so what from CS61A does this remind you of? Recursion, right? And that's by design. Okay? So induction is a very structured proof technique. Okay? Whereas, sometimes when we did direct proofs or we did proofs by contradiction, we knew that was the structure, but we didn't really know how to proceed with the proof, right? The actual structure we use for the proof could be anything. We could have used any, branch of mathematics. With induction, it's extremely clear. This is your first step, this is your second step, and this is your third step. Okay, so the proof is very structured for you. Okay, and all induction proofs will have exactly these 3 steps. Okay, first you'll establish your base case, just as you do in recursion. Okay, and what you want to do with the base case is establish that your statement holds for either n is equal to 0 or n is equal to 1 or whatever you're told in the problem. Okay, sometimes you'll be asked to prove some property for all natural numbers greater than or equal to 3. And in that case, your base case will be when n is equal to 3. Sometimes you'll be dealing with all whole numbers and you'll use n is equal to 0. And sometimes you'll have to infer from the context of the question, right? If your question, involves a sum that looks like I is equal 1 to n, your base case can never be n is equal to 0, because what does a sum going from I is equal 1 to 0 look like? That's not really defined, right? So in these cases, your base case will almost always at least be 1. N is equal to 1, that is. Okay? So first you have to establish your base case and prove the base case holds. And usually, this only takes one line. Okay? Usually, very simple. Okay? So you establish that the base case holds. The second step is really more of a formality. You need to write that you're assuming that the proposition that you're trying to prove holds true for some arbitrary value k, where k is a natural number. Okay? You can't assume a particular value of k. You just explicitly have to say, assume that the statement holds true for n is equal to k, where k is some natural number. Okay? And most of your work will be done in the third step. Okay? What you need to do in the third step is, given your assumption that the statement holds when n is equal to k, you need to prove that it holds when n is equal to k plus 1. Okay? So you take your induction hypothesis that the statement holds when n is equal to k, and use that to prove that it holds when n is equal to k plus 1. And if you if you show that this is true, i.e. you show that p of k implies p of k plus 1, where p is your proposition, that's what we're doing in our induction step. And a little later, after we look at our first example, we'll formalize this a little more in terms of propositional logic and look at why exactly this works. But are there any questions regarding the 3 steps of induction? Okay, every question you'll ever have to do with induction will have these 3 steps. Okay, the steps you do within the induction step will obviously be different from proof to proof, but the outline will be the same. Any questions? Okay, so the best way we're going to learn induction is by doing examples, and essentially all I have planned for today is we'll go through probably 5 examples of proofs by induction, okay? And for each of them, except for the first one probably, I'll give you a minute or so, maybe a little longer than a minute, but I'll give you some time to attempt the proof on your own with those near you, and then we'll take it up. Sound good? Okay, so the first one that we want to prove is prove that the sum of the first n natural numbers, right, is equal to n times n plus 1 divided by 2. Okay? This is an identity that you will definitely have to remember moving forward, and it will appear again in your homework. And next Thursday, when we look at different ways to derive things like series and sequences, and we look at things like telescoping sums, we will see this again and again. This is something that I highly recommend you remember moving forward, okay? Because it will come very handy, both in this class and in future classes. Okay? So what we want to prove is that the sum of the first n natural numbers is equal to n times n plus 1 divided by 2. Okay? And so let's get into it. So what's our first step? The base case. Okay? And that's never going to change. Here, what does an appropriate base case look like? N is equal to 1. Right? It wouldn't make sense for n to be 0. You can't take a sum going from I is equal to 1 to 0. The base case that makes the most sense here would be n is equal to 1. So let's just say n is equal to 1. And what I like doing is showing that the left side and the right side both evaluate to the same thing, using this little table. Okay? So what does the left-hand side of the expression look like? Well, it's just this, right? The sum from I is equal 1 to 1 of I. Well, that's just a sum of one term, which is just the term on its own. Pardon?
What is that?
Left side and right side. Yeah. Okay? So I've shown that the left-hand side of the equation is equal to 1 when n is equal to 1. Now let's look at the right-hand side. Well, I have this expression, right? N times n plus 1 over 2, but in this case we're setting n be equal to 1. So in this case we'll have 1 times 2 divided by 2, which is also equal to 1. And here we see that the left-hand side and right-hand side are the same, therefore the base case holds. To write it a little more explicitly, left-hand side is equal to the right-hand side, therefore base case holds. Any questions with that? Okay, now let's look at our induction hypothesis. Okay? Now, in our induction hypothesis, all we have to do is state that we're assuming that this proposition holds true for some arbitrary value k, where k is also a natural number. So assume that this sum for some okay, so literally that's the entire induction hypothesis. Assume that the sum of the first k natural numbers is k times k plus 1 over 2 for some arbitrary natural number k. Okay? And now, I guess I can write 1, 2, and 3. Now it's time to actually do the induction step where we do the bulk of the work. Okay, so one thing we have to be careful of is what we should do is start with one side of the expression and make it look like what we want to look like. Okay, one common mistake that people make is that they start off by assuming the statement holds true for n is equal to k plus 1. That's what we want to prove. Okay, so you can't start off by assuming that. So what we want to show that this holds true. We want to show that when you sum from I is equal to k plus 1 of I, you get k plus 1, k plus 2 divided by 2. Okay, that's our goal. But all we can do is either start with the left-hand side of this expression and show that it equals the right, or start with the right-hand side of this expression and show that it looks like the left. Okay? There isn't really much we could do if we started off with the right-hand side of this expression. So what we'll do in almost all cases when we're dealing with the sum is start with the left-hand side of the expression. Okay? Let's start with the sum itself. Okay? And what we know is we want to use our induction hypothesis in some way. Right? So how can I rewrite this sum going from I is equal 1 to k plus 1 in a way that would allow me to reuse my induction hypothesis? Any ideas? Yeah.
You could write it as the sum of I equals 1 to k plus k plus 1.
Exactly. So to make that a little more explicit, I know I can write this sum as 1 plus 2 plus dot 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 plus k plus 1. And I can break this apart into two separate sums. One being this first thing that I've already seen, plus this last term, k plus 1. Okay? And the sum that I've underlined here, that's what we saw in our induction hypothesis. And we're assuming that to hold true in the proposition that we want to prove, right? So what I can say is that this sum is equal to k times k plus 1 over 2 plus k plus 1. And oftentimes you'll see by induction hypothesis. Is that clear? So in the induction step, you will always somehow utilize your induction hypothesis. Okay? And now, what I want to do is show that this expression that I have here looks like k plus 1 times k plus 2 divided by 2. Okay? So how can I do that? Well, how could I bring this expression to a common denominator? Well, I can multiply the second term by 2 over 2, right? And then on the denominator, I would have 2, and I can take out a common factor of k plus 1. Actually, to write it a little more explicitly, I could add this, which, taking out the common factor of k plus 1, I would get k plus 2 divided by 2, which is exactly what we wanted to show. So to recap what we did, we showed that the statement holds when n is equal to 1, so our base case. Then we stated our induction hypothesis, so what we're assuming to be true, which is that the statement holds for some arbitrary value k. And then in our induction step, we're showing that if it holds true when n is equal to k, then it implies that it holds true when n is equal to k plus 1. And what we did is we started off with the sum of the first k plus 1 natural numbers, broke it down into two components. One, which is the sum of the first k natural numbers, plus k plus 1. And with the sum of the first k natural numbers, we were able to use our induction hypothesis in this line to help simplify things and rewrite the sum as what we wanted to show. Okay, so it's important to see here, we're not assuming the statement to be true for n is equal to k plus 1. We're assuming it to hold true for some arbitrary value of k, and then showing that if it holds true for this value of k, then it holds true for k plus 1. So any questions with the mechanics of what we just did? Okay? Don't need that. And so maybe this will make things more clear, in terms of propositional logic. Okay? So suppose P represents the proposition we're trying to prove true. Okay, maybe we could say P of n. And so our base case involves us showing or proving that P of 0 or P of 1 or whatever the base case in our question is holds true. Okay? In the last example, it was P of 1, right? Because it didn't make sense to take the sum when n was 0. So in that case, we showed that P of 1 held true. And then in our induction hypothesis, we assumed that P of k held true. Okay, for some arbitrary value of k that we didn't assume anything about. Right? Back here, we didn't say k was equal to 10 or 15 or anything. We just said k is some arbitrary value, and let's assume that the statement holds true when n is equal to k. Then in our induction step, we showed that if P of k is true, that implies that P of k plus 1 is true for any arbitrary k. And so what we have now, putting together the fact that the base case holds true, and that if arbitrary k is true, that it shows that arbitrary k plus 1 is true, we get this chain of implications. It shows that if the base case is true, then, the base case plus 1 is true. Well, if base case plus 1 is true, we've shown that base case plus 2 is true, so on and so forth. And so we use this to prove that the statement holds for any natural number. Is that clear? So we're showing the base case should be true. And then we also showed that if P of k is true, it implies P of k plus 1 is true. And so what you can say is that you can plug in k is equal to 0 here. And we know for sure, because we concretely showed that P of 0 is true, it will imply that P of 1 is true. And then we plug in k is equal to 1. And it gives us the implication of P of 1 going to P of 2. So the base case is important in that we need to know that the very first thing is true in order for this chain to work. Because if we don't know that the base case is true, then it doesn't, for example, the implication false implies anything is always true, right? So we need to show this base case to be true first. Otherwise, the implication may still be true, even though the successive propositions themselves aren't true, right? So we show the base case to be true and show that we can jump from n is equal to k to n is equal to k plus 1. Putting those two things together, it says it proves the statement for n is equal to 0, n is equal to 1, n is equal to 2, n is equal to 3, so on and so forth. So any questions with this? So we prove our base case, and then prove that we can jump from n is equal to k being true to n is equal to k plus 1 being true. And as long as we've shown concretely that that one base case holds true, we've shown that it holds, that in combination with our induction step, proves it for all natural numbers. Is that clear? So any questions with this idea? Okay? And I agree, this looks a little abstract when you just look at it on its own. And so the best way to learn how to do induction is by working through examples. Okay? And it will become more clear, the more examples we do. Is that clear? Okay? And a lot of your homework this week will just be pounding through examples of problems using induction. Okay? Cool. So let's look at another example. Okay? And this one, I'll allow you to work on it for a couple minutes on your own, see where you can get. So first, De Moivre's theorem, which you might have seen if you studied complex numbers before, or maybe in E16b, but it's not really that, complex numbers are really not that relevant to the question. It states that if you take a number of the form r times cos t plus I sine t, and raise that entire number to the n, the nth power, you get r to the n times cos of n times t plus I sine n times t, where I is the imaginary unit. Okay? And so what we want to do is prove that this statement holds true for all whole numbers. So now we're starting with n is equal to 0 using induction. Okay? And the hints I will give you, you will need the following two rules. The sum of cosine identity and sum of sine identity. You'll need to use that in your induction step. Okay? So I'll give you a couple minutes, play around with it, see where you get, and then we'll start talking about it together. Discuss. Oh, this should be a plus. There you go. Okay, let's come back together and work through it. Okay, so what will our first step always be when we're working with induction? The base case, cool. And in this case, it looks like that will be n is equal to 0. Because we're told that we're looking at all whole numbers n. The statement actually holds true for all integers n, but we're not going to prove that. Okay. And so let's again look at left side versus right side. Well, what's the left-hand side? Well, it's r. It's, I guess we can put parentheses around here. R cos t plus I sine t to the exponent 0, and anything to 0 is 1. Cool. What's the right-hand side? Well, it's r to the 0, which is 1, times cos of 0t plus I sine of 0t. Okay, well, r to the 0 is 1. What's cos of 0? That's also 1. And sine of 0 is 0, so the I doesn't really do anything. We're left with 1. And then, so since we have the left-hand side is equal to the right-hand side, we can say the base case holds. Okay? And I want you to get in the habit of explicitly writing base case this, therefore the base case holds. Induction hypothesis is this. Induction step is this. Okay? Because not only is it important in this class, but in future classes, this is something that they will emphasize. Okay? So it's better to just learn it now. Okay? What's our next step? It's our induction hypothesis. I think I gave us an extra slide here. Yeah, we're good. Our induction hypothesis, which is what? What's our induction hypothesis? Not that it holds for any n. It's that it holds for k, where k is some arbitrary integer. Or arbitrary natural, or whole number, I guess, in this case. Okay? If we said that our induction hypothesis is that it holds for any n, we're assuming it to be true already. We're saying that it holds for some arbitrary value of k, where k is a natural number. It's important that we're using k instead of n here, because n is what our proposition is in terms of. K is just, we're saying, is some arbitrary number in the set of naturals or whole numbers that we're assuming that it holds just for this arbitrary value of k. Okay? So we're going to assume proposition holds for n is equal to k. In other words, we're going to assume the following is true. R times cos of t plus I sine of t to the k is equal to r to the k cos of kt plus I sine of kt. Does that sound good? And now let's look at our induction step. How do we do this? Okay, let's give us some more room. Now let's look at our induction step. Okay, what we want to show, another way of putting that is what we're required to prove, is the following. Write our t a little differently. T plus I sine 1 of t. Okay? And again, we can start from one side of this expression and work towards the other, or vice versa, but we're not assuming that this holds already. We need to show that it holds. Okay? So what we'll do is start with the left-hand side and show, using our induction hypothesis, that it's equal to the right-hand side. Okay? And so what I'll actually do, just to free up some space, is remove this, because we kind of already know what we have to show here. And again, we want to show that it looks something like that. Okay? So what's one step that we can do that will allow us to use our induction hypothesis? I kind of wrote the hint in the top right corner over here. We have it written as something to the exponent k plus 1. Yeah, do you want to finish that?
Yeah, so basically we just like take that to that exponent and then have like set equal to 1 for the next sort of expression and substitute that.
So what you're saying is break this apart into r cos t plus I sine t to the exponent k times r cos t plus I sine t with exponent 1, right? And so this is a common theme, right? Notice back when we did this sum over here, we took a sum that went from I is equal 1 to k plus 1 and broke it apart into 1 to k and then the last term, right? So we this is a common trend. We'll break apart k plus 1 into k, which will allow us to use our induction hypothesis, and 1. Right? We did that in this question here. We broke the sum from I is equal 1 to k plus 1 into the sum of the first k and then the k plus first term. We're doing that again here. We're taking something to the exponent k plus 1 and rewriting it as something to the exponent k times something, right? And why did we do this? Well, it's because here we can use our induction hypothesis to simplify things. Okay, the whole point is that in your induction step, you want to use your induction hypothesis. Okay, and so what can we do? We can replace this with r to the k cos k of t plus I sine k of t. And now we have to multiply that by this thing at the end. Sound okay? And well, we have r to the k, and like this is just multiplication between all of these things, so we can rearrange as we want. And so I can take the r to the k and the r and write that as r to the k plus 1. Okay, and then now I will have this relatively large product of 4 terms. Okay, so when I multiply cos kt and cos t, I'll get this term, cos kt cos t. When I multiply cos k of t, cos kt and I sine t, I'll get something that looks like, plus I cos kt sine t. And I multiply these two terms, and I can put the I, like group the terms with the I. Plus, now I have I squared sine k of t sine t. Is that clear? And now I need to simplify this to make it look like the proposition. Any questions with where we are so far? Okay, so what's one simplification we can make? Well, we know I squared, the way I is defined, it's such that I squared is negative 1. So we can replace the I squared with the minus sign. Okay? And so I can write this as r to the k plus 1 cos kt cos t minus sine kt sine t plus I times whatever we had before. Should I write this a little differently? Lots of K's and T's, but hopefully we're still good. And now we use the hint that I provided originally, right, for the sum identities for cosine and sine. Okay, so first we'll use the identity for the cos of a sum. So what we can say is that cos of kt plus t should be cos of kt cos of t minus sine of kt sine of t. That's just a direct application of the rule I wrote on the last slide. It's totally fine if you didn't remember this. I had to look it up right before this as well. It's not something that you really need to remember, but I mean, it's given to you. And that tells us we can write this first term as cos of kt. Cos of k plus 1t, I should say. Is that clear? Because, of course, we have cos of k plus 1 t. We can break apart the k plus 1 t into kt and t. And then we do the same thing for the sine one. Right? We know that the sine of k plus 1 t is sine of kt plus t, which is exactly what we have down here. Sine of kt cos t plus cos of kt sine of t, which tells us we can plug in I sine k plus 1 t down here. And we're done. Okay, because we assumed that it holds true when n is equal to k, and using our trig identities and the induction hypothesis, we showed that if it holds true when n is equal to k, then it holds true when n is equal to k plus 1. And we've shown exactly what we wanted to show. And so we can say, therefore, induction holds. Is that clear? Yeah.
For the very first induction step, can you explain how you multiply the second factors?
So are we looking at this line here?
Yeah.
Okay, so are you okay with how I expanded the k plus 1 into these two terms?
Just in the first term. I'm not sure how you got to the second term.
So is your question about this?
Oh no, it's still on the first line. How did you get the second term? Yeah.
I see. This is box to the exponent k plus 1. Do you agree with that? And anything to the exponent k plus 1, just by the exponent laws, is the same thing to the exponent k times the same thing to the exponent 1. Is that clear? Cool. Any other questions with the mechanics of what we did here? Yeah?
So when you were to write my induction hypothesis, would you write that in the
Oh, therefore induction holds? Oh, you're saying here. Here. By induction hypothesis?
Yeah.
Yeah, that, like, writing by induction hypothesis isn't necessarily necessary. I think it's a good practice, though, especially in the beginning, just so it makes it explicitly clear to yourself where we're using the induction hypothesis. Any other questions with this? So I agree, in this example, there's a lot to take in. Like, it's probably been a while since we used these kinds of identities, but I think that illustrates how interesting induction is, right? Like, normally, when you would look at de Moivre's theorem, you would look at, this is an aside, but you would prove it by showing that this is true, which is true by exponent laws, right? And the I theta is just cos of theta plus I sine theta, right? But we've proven the exact same thing using induction, which I think is interesting. Okay, so you can really use induction to prove statements in all sorts of branches of mathematics. Any questions with this? And actually, I believe on the homework, there will be two interesting questions. One, you'll prove the power rule for taking derivatives using induction. And you'll prove that, I believe it was the sum of the interior angles of a polygon is 180 times n minus 2, also using induction. Okay, so induction can really be applied to all branches of mathematics. Okay, let's move on into another example. This one deals with the Fibonacci sequence, okay, which you've likely seen before. It's one of the first things you implement recursively in 61A along with the factorial function. It's defined by this recurrence relation where the first two terms are equal to 1, and f of n is equal to f of n minus 1 plus f of n minus 2 for all n greater than or equal to 2, n being a natural. What we want to prove is that the sum of the first n Fibonacci numbers is the n plus 2th, or n plus 2nd Fibonacci number minus 1. Okay, so this one's a little more straightforward than the last one. So again, I'll give you a couple minutes to try and work it out and see if you can complete the proof. And again, this should be like a group activity. Just give me 1 second. Okay, let's come back together and walk through this one. Okay, so again, let's see if we can the page. No. This will follow the same framework. Okay, what's our first step? Base case, great. Okay, here, Fibonacci numbers aren't really defined when n is, 0. And if we, let n be 2, in this case, we'd be skipping something. So the very first, possible value for which this statement could hold is n is equal to 1. Okay, so let's again look at this left side, right side thing. What's the left-hand side? Well, it's the sum of just the first Fibonacci number, which is what? 1. Okay, the right-hand side is f of 1 plus 2 minus 1, which is the third Fibonacci number minus 1. And it looks like the third Fibonacci number is 2, and 1 less than that is 1. So we've shown that the base case holds. Does this sound good? Okay, so therefore, base case holds. Great. Now let's do our induction hypothesis. Okay, so we'll assume that the sum of the first k Fibonacci numbers is equal to the k plus 2 Fibonacci number minus 1. Where k is some arbitrary integer. Is that clear? Now we're looking at the sum of the first k plus 1 Fibonacci numbers, right? So we want to show that the following holds. Okay? This is what our goal is, but again, we can only start with the left-hand side and manipulate our way until we get to the left, or start with the left-hand side and manipulate until we get to the right. Okay? We can't start off by assuming that this statement holds. Okay? So what I'll do to make that extremely explicit is just erase the right-hand side of the expression. Okay, just so we don't, accidentally assume that to be true or anything. And what will we do? How can we proceed from here? Again, this is a common theme. Yeah.
You can do the sum up until k plus k plus, or f of k plus 1.
Good. I can break apart this sum into the sum of the first k Fibonacci numbers plus Fibonacci number k plus 1 on its own. Is that clear? Cool. And now we can use our induction hypothesis, right? What does our induction hypothesis say? It says that the sum of the first k Fibonacci numbers is f of k plus 2 minus 1. Is that clear? So I can substitute in my induction hypothesis. Again, just to make it extremely explicit. Okay, and now what can we do to complete the proof? Yeah.
Use that formula that you got up there and then add the x.
Good. So what I can use is just the property that defines Fibonacci numbers. I have f sub k plus 2 and f sub k plus 1. And I know by the rules of Fibonacci numbers, if I add two consecutive numbers, I get the next number of the sequence. So if I add Fibonacci number k plus 1 to Fibonacci number k plus 2, I will get Fibonacci number k plus 3, which is exactly what we wanted to show. We wanted to show that the expression holds true when I plug in k plus 1, given that it holds true when I plug in k. So what I can say is, therefore, induction holds. So again, base case, induction hypothesis, induction step. And I'm being very explicit in each of these three steps, when I'm doing these steps and what I'm assuming from the previous steps. Okay, and this is a habit that you need to get into. Your proofs should all look something like this. Yeah?
Can you make your base case n equals 1? But the thing says n is greater than or equal to, is that okay?
So you're saying, why is our base case You're saying, why is our base case n is equal to 1 when this property is only true when n is greater than or equal to 2? That property is only true when n is greater than or equal to, should actually say n is greater than or equal to 3. But that doesn't really change anything. That's just defining how we create the Fibonacci numbers. Okay? The fact that there's an n is greater than or equal to 3 here doesn't really play a role over here. Okay? The property that we're trying to prove can possibly hold, like it's a valid expression when n is equal to 1, and that's the smallest n for which it makes sense, so that's what we'll use. Right? We couldn't have used n is equal to 0 because there is no Fibonacci number 0, at least the way we've looked at them. Right? They start being indexed at f1. So it wouldn't make sense to sum when n is 0. Yeah?
So for induction problems, do we always start from the left-hand side and work away from the right-hand side, or is there some scenarios in which we should start from the right-hand side?
Well, I mean, that's arbitrary, right? Like I could have written this as fn plus 2 minus 1 is equal to the sum. And we would be doing the opposite, right? So usually what you do is break down whichever side of the expression that you can substitute your induction hypothesis into. Okay, and usually that'll be pretty clear. I'm not saying it's impossible to write this, like do this the opposite way. In fact, you could just do the steps in the opposite direction, right? If you started off with fk plus 3 minus 1, you could have split it apart into the previous two things and then substitute the induction hypothesis. So you can basically almost always do either way, but usually there will be one direction, I guess, that makes more sense. Any other questions? Yeah? Because that's the smallest natural number for which this is a valid expression. Okay? N is equal, like we want the base case to be the smallest possible value where this holds. Okay, so that when we have this jump from k to being k plus 1, we can start at the smallest possible number. If we instead had our base case be n is equal to 2 and then do the induction step, we didn't show anything for n is equal to 1, right? So we haven't proved it for all natural numbers where it holds, right? So here, the main reason I chose n is equal to 1 instead of n is equal to 0 is because a sum of this form doesn't make any sense. Okay, another way of looking at what this says is for I in range 1, 0. Does that make it a little more explicit? Like that wouldn't make sense in Python, right? The smallest number you could put here would be 1. Okay, it wouldn't make sense to do a for loop from i's in range 1, 0. Cool, any other questions with this? And the process of selecting a base case will become more natural the more problems we do. Okay? So we have two more examples to wrap things up. So this one's interesting because it shows that not all induction problems are necessarily purely arithmetic. Okay? So in this one, we're told that suppose that we have two n plus 1 airports, just, I don't know, on Earth, where n is a positive integer. Okay? The distances between any two airports are all different. Okay, so another way of thinking about that is if you pick any three of our airports, they form a scalene triangle. Okay, so none of the sides have the same length. Okay, so we have two n plus 1 airports. The distances between any two of the airports are all different. From each airport, there's one plane leaving from it and going to the closest airport. Okay? So we have two n plus 1 airports, all the distances are unique, and every airport is sending a plane to the closest other airport. Okay? What we want to do is, with induction, prove that there exists an airport which none of the planes are headed towards. Okay, so prove that there's an airport with no incoming planes. We're told by the problem that all airports have exactly one outgoing plane, which it's sending to its closest neighboring airport. We want to prove that there's some airport with no incoming plane. Okay? And here, what we could say is you want to induct on n. Okay, our induction is on n, not 2n plus 1. Okay, so we're still proving this property for where n is a natural number, right? Positive integers is the same thing as natural number. So, our induction hypothesis, or like our induction hypothesis shouldn't involve 2n plus 1, at least in like the thing we're assuming. Okay? So I'll give you a couple minutes to work through this, and then we'll come together and take it up. Also, while you work on this with your partners, I guess. Listen. Okay, let's come back together. So again, all induction problems will follow the same framework. Our first step will be to look at the base case, which I told you would be when n is equal to 1. And when n is equal to 1, how many airports do we have? Right? 2, 1 plus 1 is equal to 3 airports. Okay, and when we have 3 airports, well, let's just take a look at what this would look like. They form a scalene triangle, right? Because all pairs of distances are unique by what the problem tells us, right? So let's just say it looks like this. Okay, and so you can think of these 3 airports as forming a triangle, and let's look at the 2 vertices on either ends of the shortest side, right? Because there's 3 distances between the 3 airports, and we can look at the shortest side. Well, let's say this is the shortest side. What do we know? These airports are going to send their planes to each other, right? So this airport will send its plane here. This airport will send its plane here. This airport over here has no incoming planes. Okay? And this picture is more of just to illustrate it to you. But what I would probably do to write this formally would be to say, consider all 3 airports by the problem statement. The distances between these 3 airports are unique. Consider the 2 airports that have the shortest distance between airports. By the problem statement, they will send their planes to one another. And as a result, the 3rd airport has no incoming planes. Okay? Obviously, this airport will also send a plane somewhere else, probably here, but it has no incoming plane. Right? Because it is not the closest airport to any other airport. Is that clear? So what we can say is, therefore, the base case holds. Okay? Let's look at our induction hypothesis. So let's just assume, and remember I said we're performing induction, or we're inducting on n. So we're going to assume that if there are 2k plus 1 airports, that there's 1 airport with no incoming airplanes. Right? So assume statement holds for n is equal to k, i.e. assume in 2k plus 1 airports Okay, so we're saying, assume that if we have 2k plus 1 airports, there's some airport with no incoming plane. Is that clear? And now what's our induction step? Can someone tell us how to walk through this in the k plus 1 case? Sure.
So you would consider it when it was, so you would end up having 2k plus 3 airports?
Yeah.
And so you would want to consider the case when you have 2k plus 1, and you know that in that case there is an airport that has no planes arriving to it.
Okay.
And so now you have 3 airports, and only 2 planes arriving between those 3 airports. So that means not all of those 3 airports left over can get a plane.
Yeah, that's almost essentially right. We would say in the opposite direction, like we would start with 2k plus 3 airports, and I'll go over this a little more in just a second. We would start with 2k plus 3 airports, say that since all distances are unique, there's the shortest distance between the 2 airports, right? And so those airports will send planes to one another. And then, now we just have to consider the remaining 2k plus 1 airports, which, from the induction hypothesis, has an airport with no planes coming into it. Did you have something at the back? No? Okay, yeah. But that's essentially the general idea. We're going to consider any 2 airports. We know that if they have the shortest, let's consider the 2 airports with the shortest distance amongst all the distances. They will send their planes to one another, and then now we can just look at the remaining 2k plus 1 airports. Yeah?
Can you explain, for example, that one airport that was before 2k plus 1 was not sending in airplane?
Yeah.
So that was not receiving an airplane?
Yeah.
So if we add 2, isn't there a chance that one of them is going to send it to that one?
Yeah, and so that's a very good point. And that's exactly why we don't start with the 2k plus 1 airports and add 2. We start with 2k plus 3, which we're not assuming the statement to be true for. We're just starting with 2k plus 3 arbitrary airports, looking at the 2 closest, and then removing them. And now we have a set of 2k plus 1 airports, right? And so that's a very important point, and I'm glad you brought that up, because that would be very prevalent in future courses when you talk about graph proofs. And when you do proofs on graphs with induction, what you'll always have to do is start with the larger graph and then remove something. Okay, you can't start with the smaller graph and then add something, because what you're assuming about the structure might not hold true when you add an additional node in your graph. Okay, so again, what we want to do is consider 2k plus 3 airports, then consider the 2 airports closest to right? So we want to consider the two airports that are closest to one another. By the problem statement, this is unique. Okay, and then we can effectively remove them because all we care about is planes, like the incoming planes to each airport, and we know both of those nodes have an incoming plane, so we can effectively ignore them. Running out of space here. What that says is now that we've effectively ignored the two airports that are closest to one another, because we know they'll each have an incoming plane, so let's put them aside and consider the remaining two k plus 1 airports. By the induction hypothesis, if we have any set of two k plus 1 airports, there will be a plane in there, an airport in there, with no incoming plane. Okay, so therefore, we've used the induction hypothesis to show that the statement holds true when we have two k plus 3 airports. And so what we could say is, therefore, induction holds. Okay? And so this example of, airports and planes really is just an abstraction for graphs with nodes and vertices. But we don't have to worry too much about that for now. But this general idea of starting with the larger graph or starting with the larger situation and then breaking it down into a smaller one where we can still assume the structure is important. Okay, let's not pack up just yet. I still have one more example that I want to look at, which will be very relevant to the homework that you'll have coming up. Okay? And this one I'll sort of just walk through it right now. What we want to prove is that 8 divides 9 to the n minus 1 for any natural number n. Okay, we want to prove that 8 divides 9 to the n minus 1. Okay? And when we get to modular arithmetic and look at how we could rewrite 9 in terms of modulo 8, this problem will greatly simplify. You can do it with one line. But we can also do it with induction right now. Okay, so we don't need to worry about modular arithmetic for now. Okay, we want to prove that 8 divides 9 to the exponent n minus 1 for any n. So another way of writing this is that we want to show, and this is an if and only if, right? We want to show that we can write 9 to the n minus 1 is equal to 8c, where c is an integer. Is that clear? Those are equivalent conditions. Right? Okay. Let's dive into it. What's our base case? We're told we're looking at natural numbers, so the natural, no pun intended, base case is n is equal to 1, right? And let's do it. Well, what's 9 to the 1 minus 1? Well, that's 8. And pretty trivially, 8 divides 8, because you can multiply it by 1 and you'll get 8. So, therefore, base case holds. And remember, if you ever forget what the divides notation it just means the left number is a factor of the right number. Okay? Induction hypothesis. Just assume 8 divides 9 to the k minus 1. Is that clear? Okay? In other words, we can say 9 to the k minus 1 can be written as 8c. And now, in our induction step, we want to somehow use this. Okay, we want to show that we can write, we want to show that 8 divides 9 to the k plus 1 minus 1, i.e. we want to show that we can write 9 to the k plus 1 minus 1 is equal to 8 times, b. It's not going to be the same c because it's a different number. But we just want to show that we can write 9 to the k plus 1 minus 1 as 8 times some integer. Okay, so let's start with 9 to the exponent k plus 1 minus 1. Again, very common theme. We break up a k plus 1 into a k and a 1. So we'll write this as 9 to the k times 9 minus 1. Okay, how can we proceed from here?
1 plus 2.
Yeah, we can write 9 to the k as 8c plus 1. Is that clear? Because writing 9 to the k minus 1 is equal to 8c is the same as writing 9 to the k as 8c plus 1 times 9 minus 1. And then we can write this as 9 times 8c plus 9 minus 1. Now I just distributed the 9. And to make it a little more clear, I can write this as 8 times 9c plus 8, which I can then write as 8 9c plus 1, which I've done what I wanted to do now. I've written 9 to the exponent k plus 1 minus 1 as 8 times some integer. Right? Therefore, induction holds. Okay, our goal was to write 9 to the exponent k plus 1 minus 1 as 8 times some integer, and we did exactly that. Okay, that's it for today. Next week on Tuesday, we'll introduce this idea of strong induction. Before, or like I guess today, all we assumed was that the proposition holds for p of k. But sometimes we want to assume more than that. Like the proposition holds for p of k minus 1 as well. And so we need this thing called strong induction. And we'll also look at various proofs with induction and look at the flaws in them. Okay? Also, the textbook has several examples of induction problems. So if you want more examples of proofs with induction, feel free to look at that.